Like always, welcome to the AI for EU Cafe. Again, we start slowly. Most attendees need about some minutes to come in, but who is already there? Great that you came today. Our live presentation will be today from Wilselek, and I will slowly in the next 2 minutes, 3 minutes, will introduce him. But our theme today is understanding the world with AI, training and validating AI systems using synthetic data. My name is Carmen McWilliams. I'm your host, and please take the notice as we see on this slide. This session will be recorded. I will now start with the recording if you are notified. This recording is available afterwards to all the participants. And please, no confidential information shall be shared in this cafe session. All speakers express their personal views and opinions. This is not the official AI for EU project opinion. So everybody is here free to say what they want. And see, now we have a nice audience. Thank you again for coming. We are here in the cafe with the title Understanding the World with AI, Training and Validating AI Systems Using Synthetic Data. And once more, for everybody in the waiting time, what is the AI for You Web Cafe? The Web Cafe is public and offers a series of live web sessions on AI. Please join us in our online cafe to gain insight into the European AI scene, share knowledge and experiences, and meet stakeholders from various areas of AI research. Again, also, if you want to interact, this is a webinar, which means it's in the beginning one way. We will make presentations, and afterwards there will be a question-answer session. You may ask questions by writing them down. On the right side, there's a control panel. If you like, you can write them, but you can also raise your hand. There's a little function button with a hand. So if you wish to speak, this is also possible after the presentation. The presentation altogether will be 1 hour today. This is about the idea of the whole session. And I now want to start. It's now 3:04 to introduce our great speaker, Wilselek, which we see already with the webcam.
Hello, everyone.
Hi. And here I have a gigantic CV, but I'm going to tell you the beginning. If you want to find out more, you should ask Philip. So Philip Wilselek is scientific director at the German Research Center for Artificial Intelligence, the DFKI, where he is leading the research area Agents and Simulated Reality since 2008. He is the site director of DFKI Saarbrücken and a member of the executive board of DFKI. He has been director for research at the Intel Visual Computing Institute, a central research institute of Saarland University, co-founded by Intel from 2009 to 2017. He is the principal investigator at the Saarbrücken Cluster of Excellence on Multimodal Computing and Interaction. At Saarland University, he has been a full professor of computer graphics since 1999. Before coming to Saarland University, he was a visiting assistant professor at Stanford University, USA. He studied physics in Frankfurt and Tübingen and got his PhD in computer science from Erlangen University, Germany. This is impressive, and there's much more to say, but I think this is for our short time nearly impossible. So I will now hand over the mic and, of course, the camera and the presentation to Philip, and he will probably now introduce himself and tell us what he wants to present. So one moment, everybody with us. I change now the presenter to Philip. He from then on can do it. So Philip, now we should be capable to show your screen. Please.
Do I still need to press the button, right?
I think we see it. It's perfect. We see it. So.
And you hear me too?
Yes, I hear you. I see you. I see your presentation. I think we can start. Thank you.
Okay, perfect. So first of all, welcome for everyone from my side as well. Again, my name is Wilselek, Scientific Director at the Research Center for Artificial Intelligence. As Carmen just said, I'm also professor for computer graphics at Saarland University. One aspect that might also be interesting is that I'm one of the members of the high-level expert group on AI, which is advising the European Commission on AI, and I'll talk a little bit about CLAIR a little bit later. So the topic is digital reality. I kind of added this digital reality to it, understanding the world with AI using synthetic data. And so I need to get my mouse to the right place. Okay, the overview, I'll talk about how we first of all, I start with some background information about myself and where we're coming from and what we're doing in general, and then I'll talk about this concept of digital reality that we use for understanding the world with AI, in particular the use of synthetic data for training and validation, how we use AI to optimize and safeguard other AI systems, and not just achieve functionality on the AI side, but also are able to certify the AI system. Then I'll briefly go into some of the applications, mostly in the context of autonomous driving. And if there's time at the end, I'll also look into talk a little bit about explainability of AI before I conclude. So very briefly, I'm coming from DFKI Saarbrücken, which is on the Saarland Informatics campus here on the campus of the Saarland University. We have the university here. We have two Max Planck Institutes in computer science here, which obviously focus on basic research, and the DFKI, which obviously, as you might know, is focusing more on application-oriented research in AI, of course. Together, these four institutions work really well together. So the cluster of excellence, the Intervisual Computing Center that Carmen mentioned before, were all outcomes of this collaboration. And the latest part of this is the new Center for IT Security, which is a Helmholtz Center, will grow to 500 to 600 people. So there's a lot going on here on campus. Just to briefly show you, this was computer science 10, 12 years ago. Since then, we've essentially built a new building for computer science every year, and we're already planning for some other ones. So there's a lot of stuff going on. So what is DFKI? As far as we know, it's still the largest research center worldwide. We're already 31 years old by now. And then this largest research center is despite the huge investments in the US and in China. And we're growing very quickly. We have now 6 sites, Saarbrücken, Bremen, Kaiserslautern. Saarbrücken is the largest one here where I come from. We also have sites in Berlin and Osnabrück and Oldenburg, so all in Germany. 18 research areas, which are pretty autonomous, each one of them, and 10 cross-cutting competence centers, for instance, for specific topics, so including, for instance, deep learning or autonomous driving. DFKI is, the number is actually a little bit old by now. We crossed the 1,100 employee limit a month or two ago. And we created a lot of spin-offs over our lifetime, most of them actually in the last few years. What's interesting also is that DFKI, we're not a purely academic organization, but we're actually a non-profit GmbH under German law. So a company, essentially, research company, if you want. Our shareholders are the universities, as well as you can see here, essentially many companies from Microsoft, Google, Intel, SAP, a lot of companies from the automotive area, Airbus, but also financial area like München Rück or the Deutsche Börse and others. All of the scientific directors at DFKI are also professors at the local university, and so there is a very tight integration between what we do here at DFKI and the research side, the academic research side at the university, which is really a very nice setup, I should say. This slide kind of shows a little bit how we're operating at DFKI, because I think the context is important for some of the stuff I will talk about later. We're not doing the blue sky basic research only, where you do research because no one has done it before, but our focus is really here in the center on applied research and development. Then we go to basic research if the applications we're looking at require that. Right? So we always have applications in the background and motivating us. And then we, of course, do the transfer to industry. This is one of our main objectives, sorry. But we're not doing the commercialization and exploitation. We leave this to spin-off companies, to shareholders, or industry partners in our projects. At every point in time, DFKI is doing between 250 and 300 projects. So it's a fairly big organization and a lot of stuff going on at every point in time. DFKI is very international, so you see a quick overview, probably too old by now. But this is a very, very well distributed set of people from all over the world. And this, of course, also results in a fairly good network of partners that we interact with. I want to take 2 minutes or so to quickly talk about CLAIRE, because that is also one very strategic activity that we're doing at DFKI. The AI space in Europe was very fragmented, and we started to found this CLAIRE organization, the Confederation of Labs for AI Research in Europe, last year. This has grown tremendously. We now have offices in many important cities, and there's more coming. We have over 3,200 experts already. We have strong support by many of the research organizations, also including AAAI. And we already have support by 9 European governments, which I think is important. And there's also a few more in the pipeline, including hopefully Germany and France, which looks pretty good right now. What's the goal of CLAIRE? To really bring this together, European AI, to create networks. We do this at 3 levels. There is the network of research labs, which probably is more like 340 or so, and maybe even more. So this is essentially growing every week. This is like all of the existing research labs. So if you are part of a research lab and you're not part of CLAIRE yet, I would like to encourage you to think about becoming an individual supporter in CLAIRE, as well as maybe signing up your lab as a member of this network. You see the URL where you can do this up here. Then most activity right now is creating these centers of excellence. There was an important call for creating such networks of centers of excellence, the ICT 48 call by the European Union. CLAIRE has been a key part of many of the proposals. So there's a lot of stuff going on there. These will be local centers of excellence, specializing, having lots of resources, hopefully, going forward, and really linking across many of the labs in the region and nations in Germany, in Europe, of course. And then we're arguing for a European hub, what I like to call the CERN for AI, this idea of having a single location as a symbol for European excellence and ambition in AI, really an attractor also for talent, so people don't leave Europe for Google and other places, but hopefully we have enough really challenging, big support for very challenging large projects. So this is something we're still working on. We're very good collaborations, for instance, with ESA, the European Space Agency. Here's a quote from the chairman or director general. I think this is very nice. We actually had workshops with them, and they have now defined like a strategic research program with them, and they're now actually funding AI research programs out of ESA. So if you're working in this field or interested, I encourage you to look out for these calls. We're also now starting to build industry networks. Here's some of the companies we're talking to, but this is a very new area of activities. And yes, so the idea is a little bit to, in addition to CERN, ESA, and Airbus, maybe have human-centric AI as a fourth major research success story going forward, but that definitely requires a lot more work from all of us. So after this, let me quickly talk about what we're doing. Agent simulated reality, actually, let me skip this one. We've, for instance, used multi-agents technology to control an entire steel mill. We've done work which is a little bit more on my graphics side, real-time ray tracing, but I'll show you later why this is relevant for AI. And this is technology. This is now commercialized for some years now by Intel, NVIDIA, and many of my PhD students actually are working in these groups now. Actually, we developed some hardware activities, which actually was predecessors to the ray tracing hardware. This is now in latest NVIDIA GPUs, of course, in a much improved way. We're still working a lot of compilers for really with high efficiency targeting CPUs, GPUs, and now also FPGAs as a proof of concept, really achieving partially even better performance than the hand-optimized code with much less work. We're working with, for instance, material scientists to understand the microstructure of materials that determine their properties using AI methodologies. We're working in life sciences. Don't really have much time to go into this, but just give you a quick insight. We work, for instance, with simulation of human workers in factories. This is with Daimler, the large EU project now. We're working collaborative robotics with Volkswagen and Airbus. And again, the robots need to understand the human, create a model of what the human will be doing in order to collaborate. And we're doing a lot of work in autonomous driving with TÜV, with the car manufacturers, as well as the suppliers. And I want to really talk a little bit more about this area, or at least use this as a motivation for a key problem in AI that I want to address. And this is this idea of what we call digital reality, using AI to optimize and safeguard other AI systems using synthetic data. So let me quickly go through this big idea, which is driving a lot of the individual research projects. And I will use, as I just said, autonomous driving as an example, but we'll see it's not just limited to that area. So some of you might have seen this picture. This is the woman which was, I don't know, half a second later hit by an Uber car that was in autonomous driving mode. She actually had crossed 4 lanes. The sensors of the car have seen the woman for over 5 seconds, but the AI system decided that's not relevant, I don't have to do anything, and that woman was eventually killed. I think we all agree that, right, we need to build AI systems that will not allow such an error to happen. And while it's really, really terrible that a human life was, killed here, but I think the technical problem of this is that the development, the research team that built this AI system had no idea at the time. It took them 1.5 years to actually figure out what the root cause was. They had no idea that their system was not even able to recognize such a person and do the right thing. And that's obviously a problem, right? We need to make sure that if we build AI system, that they don't have fundamental errors such as this. And I want to talk about how we envision how we can do this using this concept of digital reality to achieve trustworthy AI systems. So just to formulate the problem in a little bit more succinctly here, our world is extremely complex in terms of the shapes and geometries of objects, the appearance of these objects, so colors and so on. The motion of those objects can be fairly complicated. We have to deal with weather effects, right? Wet streets look very different than dry streets. And the entire environment around this, everything is influencing things and so on. And despite all of this complexity, our AI systems must reliably make the correct decisions, right? Despite all this complexity. And a lot of these systems now use machine learning or deep learning, specifically also on the perception side. And as we all know, a lot of these data-driven AI systems, they need a lot of data, right? However, the problem is that these critical situations, and I'll take a kid running in front of a car as an example, luckily, we don't have much data. We don't want to have much data about these situations, right? And this idea of the car industry with this question of how many million miles do you have to drive until we have safe cars is just completely absurd if you think about it, because that essentially means how long do we have to drive until we've hit enough kids such that we have enough data to avoid this in the future, right? And I think we all agree this is probably not the right way of building AI systems. And so I want to argue that we need to build scalable learning platforms using synthetic data. And we actually do this in many areas of the industry already. If you think about the crash tests that the chassis of the car has to go through to be safe, right? Most of these crash tests are actually done with a finite element simulation algorithm in the computer, and only at the very end they might crash one or two cars just to make sure that the simulation actually was correct. And this is the basic approach that we want to apply to AI. So in the past, the car industry has actually done a lot of work of trying to validate cars in reality, but that's difficult, costly, and it doesn't really scale to these corner cases, to these critical situations like a kid running in front of a car, because hopefully we want to avoid seeing those accidents in the first place. So the car industry actually has started to use digital reality, so a digital model of reality or simulations of these models to actually train their cars. Now, strangely enough, what they're using to a vast degree is actually game engines. So actually the first paper published in this area was using data or image data from GTA 5, a car racing game that looked great for playing a game, but the images are not really realistic, and the human characters and the pedestrians in this simulation don't actually behave like real humans to a large degree. So while this is being used, the reality, the realism of these simulation actually leaves a lot to be desired, and that's a problem. And this is specifically a problem if you think about a very common situation that probably most, if not all of you, have seen before as you drive with your bicycle or car on the street. A pedestrian is approaching from the side towards the street, and the big question is, does that pedestrian continue walking onto the street, or will he or she actually stop? This is a fundamental question, really important, but as drivers, we hardly even think about this because we are very sure about that situation. And we actually, we don't even think about it. We know that this person will stop or will not stop. And a lot of that information actually comes from subtle changes in the motion of these pedestrians that tell us as humans that this person will stop or will not stop. So the question is, how can we get at this when we can't really create these situations by hand, because we as humans don't even know what we are recognizing there, right? So it's very hard to build these systems by an artist or something like that. So here's our general approach to all of this. So this is the digital reality concept. So we start with reality, and we're building learning models of reality in what we here call partial models. So it's not a single model about everything, but we create models about how pedestrians are moving. We are creating models about how they behave, when do they cross, depending on traffic. We're building models of how the environment looks like, how other cars and bicycles and so on are driving, and many, many other things. And the funny thing is, this is actually not work that we have to do in AI completely, because there's many other disciplines, many, for instance, in computer graphics, groups that are actually working on using machine learning for this. So we're using AI to learn models about the real world, and hopefully they're more and more accurate as we go forward. Now, when we have a reasonable description of the environment, we can use this to learn relevant scenarios, such as kid running in front of a car. Okay. Of course, there's many other such scenarios that are critical for learning to drive well. The car industry actually has an entire catalog, long catalog of such scenarios. But we're also working on using AI reasoning, validation, and verification techniques actually to make sure that we achieve the right coverage of all the possible situations, that we can identify. We can use AI to identify new critical scenarios that might not be in those catalogs yet. And we can also optimize a lot of the further processing by doing suitable reasoning before that. So then the next step is to create many concrete instances of such a scenario. The example here, the scenario is kid running in front of a car. So you might need large kids and small kids coming from left, from right, fast and slow, at day, at night, with rain, with snow, with many other variations. So there's a lot of stuff that we need to create. And then the next step is, and that's the third step, is to actually simulate these concrete instances by, first of all, simulating how the kid actually runs in front of the car, how everything else is animated in the scene, but then also simulating the sensors such that we get the data of the very specific sensors of a specific car, right, as if that car were in that situation. So we're getting hopefully a very accurate reproduction of the data a real car would be getting. Right? And now if we have that data, we can actually now simulate and train this car using this synthetic input data as if it were driving in a real situation, right? Not only can we use this synthetic data to train AI systems, we can also use it to benchmark AI systems in the sense of, right, I improve something at one point, well, let's check if all of the other scenarios it's still doing good. Maybe there's some deterioration. For other situations, we want to really check this. It's like test-driven design and software engineering. And most importantly, from my perspective at least, it is all about using this mechanism to validate AI systems. So essentially, this idea that we have in many other areas, for instance, for flying, right? A pilot for a passenger airplane is not allowed to fly such an airplane unless he is proven in many dozens of hours in a flight simulator that he can handle all the critical situations like a failing engine and all the other cases. Right? We're doing the same thing here. We're guaranteeing with many cases that our AI system will be able to handle all those situations, right? And of course, we can do this in a much more thorough way with many more situations that we can expose a human to, right? Because that wouldn't work for humans. But this is a machine, so we can actually do this with thousands, maybe tens of thousands, maybe even more cases that we can sample here. So there's a lot of high performance computing needed to do the simulation as well as the AI processing. Now, the last step is that we need to make sure whatever we've learned here actually applies to reality. So we can do this in a loop, right? Whenever we see something that we cannot interpret with what we've learned from our models so far, my prime example is a kid doing somersaults on the street, right? Maybe we have not modeled that. If you see it, our AI system will be uncertain of what it says. It hasn't understood the situation, but it knows there's something going on that it cannot interpret in a good way. So we would record this data, and that would help us build better partial models. And we have to do this anyway because the reality changes, our real world changes, right? I mean, these scooters have not been around a year or two ago. So we would have to add this anyway for as we go along, and this will certainly happen more in the future as well. So this is the general approach of digital reality. The night I explained it in the context of autonomous driving. And so but this is a very general approach, right? So if you think about it, there's nothing special in this approach that is specific to autonomous driving. The only requirement is that you are able to model the environment that an AI system interacts with. As soon as you can do that, this entire approach starts to make sense. And this is what we're pursuing. And essentially, as the FKI, as my group, Asian and Simulated Reality at the FKI, we're doing lots of projects here on the learning new models. We're doing projects on finding more critical situations and doing more efficient simulation by identifying which simulations are actually needed. We're doing work on radar simulation and other sensor simulation stuff, and we're doing work on the certification and adaptation and many other areas. So there's a lot of support stuff that's also needed. So let's look a little bit about the applications of this. And so this is not so very interactive here, but if this were an interactive talk I was given, I would ask you what you see here in the lower right-hand corner. And the usual answer is a person walking, right? And I could argue this is actually wrong because the only thing you're actually seeing is a couple of white dots moving on a black background, right? This is the real information you're getting. But my point obviously here is that we as humans, we cannot avoid instantly, looking at what is behind the data. Right? We immediately interpret what we're seeing here. We can't even avoid doing this, right? No one really sees white dots here, at least unless you do a conscious effort to focus only on the moving dots. But this is really hard to tell an AI system, right? And just with the example of the pedestrian approaching the streets, it's very subtle, tiny information, very subtle changes in the motion that tell us as humans with high accuracy that person will stop or not. And so in that sense, we have to be able to understand, understand these very subtle differences and subtle changes in the world around us, because they tell us a lot about what's going on. And we need to understand this to learn what's going on. So here is a concrete example of work we're doing. This is actually an ongoing project here. This is actually on the campus of Saarland University in front of the computer science building. There's a bus stop up here, and so people are moving on the walkways here up to the bus stop. It's kind of indicated here, but they're kind of looking backwards down the street here, whether the bus is already coming, and they might have to start running to still catch it at the bus stop. There's other people walking on these walkways here because they might want to cross here at the zebra crossing, right? But they also, of course, they turn their head to look at oncoming traffic because they might not be able to cross the street at this point in time. And you can actually see, so this is real motion capture data from pedestrians. You see the motion capture devices here on the lower left. And if you look at the blue curve, this is actually the head rotation. And you see that both the people going for the bus and the people wanting to cross essentially have more or less the same head motion, right? It's the same angle. It would be very hard to actually distinguish between the two. However, if you look at the green and the yellow or orange curve here, this is the rotation of the shoulders and the hips of the pedestrian. And you see that the person who wants to cross do something very reasonable because they want to rotate anyway to cross the street. And so when they are actually looking backwards, they already start actually rotating shoulders and hips. And now, of course, the goal is to make AI systems recognize this change in motion it is fairly subtle, but it should be recognizable. And so we do this by currently building motion models that are able to reproduce exactly this motion. There's a lot of work we've done to make this possible, the entire machinery of AI tools for doing this. And we're now in the phase of actually generating this motion and then using this to train an AI system to be able to recognize these subtle differences. This is just one of the examples of what we're doing in this context. Another example, without going into too much details because of time reasons, is actually a new, somewhat new approach to using deep learning for understanding motion. Actually, this is, I don't run the video here, but essentially what we're doing is we're segmenting motions, or we're recognizing different sorts of motion by essentially labeling the animation. So there's left and right steps, there's a starting step, there's grabbing motion, many other motion types here. And by presenting, by recording lots of motion, labeling that motion, we can actually train an AI system here at the lower part that it reproduces the ground truth very, very accurately, actually more consistently than humans can do it. But what's really interesting with this approach, it's a recent paper, is that if we don't actually have the perfect ground truth, the same thing still works. So you see the input, the training labels here in the middle, where in this case, I think it is 80% of the labels are just simple random and of course completely false, as you can see. Right? Only 20% of the labels in this case are correct. This actually still works with about 90% incorrect labels. Then we do the algorithm does some minor errors, which we know that we can remove them even. So even with essentially complete noise as input, almost complete noise as input, the algorithm actually can record the correct correspondences and still learn essentially exactly the same output as you would give it the ground truth result. So that's very, very interesting, and we're doing a lot more work in this direction now. Coming back to this mix of graphics and simulation with AI, another really interesting area of research we're doing is actually simulating sensors. And radar, while it's also an electromagnetic wave, just like light, it actually turns out that the simulation has to be quite different because we're dealing with longer wavelength. They're actually the size of objects, or centimeter, millimeters, and we have correlated photons here, which causes that we actually have to do some wave optics here, and also it turns out that optical phenomena that are less important in optical rendering are much more important for radar. And we've just actually, this is an older slide, we've just published 3 papers at SIGGRAPH, which is the top conference in this area, about new simulation techniques. And so we're working with a couple of companies now to do better better radar simulation. And you kind of see really this interplay between AI on the one hand side, creating models that we then simulate with a lot of help from computer graphics and similar techniques, simulation techniques. And of course, a lot of that needs to be supported by high performance computing. And so we're also doing that, that research, which I don't have time to go into here, but if you're interested, feel free to drop me an email. So I look at the time, and so in order to leave more time for questions, I will go very briefly through another recent project which targets explainable AI. Actually, let me skip this one. You can read it. The slides will be available, I hope. So again, we're in this highly automated driving context. And I want to talk about one very specific paper here because I think it's specifically interesting for AI going forward, right? Because we kind of have this dichotomy between learning or machine learning, and often now reduced to deep learning only, right? Versus the what's sometimes called traditional AI, which I hate this, right? At the end, we have a large zoo of AI techniques. Some are more on the reasoning side, some are more on the learning side, some are older, some are younger. Actually, deep learning goes back to the 1940s. So, but of course, there is a huge progress in this area, and don't get me wrong. We use a lot of deep learning all over the place. But what I want to argue for is that for many problems, you have to choose the best method. And here, for instance, in this project, we've actually combined a POMDP planner, that's more a traditional stochastic online planning system. Essentially, it's building some decision trees that use statistical information to make decisions. So I don't want to go into too much technical details here. And we've compared this to a deep learning reinforcement approach called NAF-A3C here. That's a pure deep learning or deep reinforcement learning based approach. And what we've done in this project is actually create a hybrid approach where we use the decision trees in the traditional POMDP planner, but we're training, right, in each of these nodes, you have decision functions, and essentially we're training in this deep learning network, we're training those decision functions within those nodes. And so it's an interesting combination between a completely free learning-based approaches and a more structured approach through that decision tree. But they're combined, and also like the decision trees are essentially providing some kinds of constraints. So even if a deep learning network here might go off the rails because we still cannot fully understand what they're doing, what the damage they could do is constrained by the more symbolic approach doing from the POMDP planner. But this is still a fully trained system. So we actually have a simulation, which we use our OpenDS system here, that we have sensor simulation models which generate observations that go here into a path planner and a belief tracker. Right? This is the tracker about what the system believes about the environment. This information then goes into this decision tree as well as the learning part, which generates an updated decision mechanism, which we then use to make decision how to accelerate or steer the car, which again tells us how to do the next simulation step. So it's really a complete simulation loop here. We're training the system to be better and better. And because of this nice structure through the symbolic POMDP planner, actually you kind of get at least a sort of explainability for free. I mean, this is not the final solution, right, for that problem, but it's a good step in this direction, I believe. And so let me skip this, the training part. We've actually evaluated this through many standardized accident studies. These are some of these predefined scenarios that I've talked about earlier. We've trained this with many scenarios, many scenes here, 40,000 scenes on a large NVIDIA DGX1 system. We added some specifically complicated cases like a pedestrian doing zigzag running here next to the road. This requires special attention, or actually having multiple people crossing the street. It turns out the deep learning system has a hard time dealing with them if it hasn't actually seen multiple person crossing the street in all of the right configurations. And the results of this is very interesting. The first is that actually this combined system can handle many more of these situations in a safe way. It's not perfect yet, but significantly better than the individual techniques here. And it is at least comparable or mostly equally competitive with regard to many of the other measures here, like time to goal, like the amount of acceleration, so the comfort of driving, avoiding misses, and many other aspects. So what I want to point out here again is it's often the combination of techniques that make a big difference. So we're doing much more work also in this area to explore this more. So this already brings me to the end of my presentation. So I think as takeaways, I want to get across that digital reality is really a fundamental tool from my perspective to model and simulate complex environments and use synthetic data to learn and reason about the scene using this feedback loop, using reinforcement learning and other techniques. So I believe this will be a key element of future AI systems. You've seen this continuous loop of learning using synthetic and real data. I think this validation that's possible through this digital reality approach will be absolutely crucial to establish trust in AI systems, because we can actually measure how good an AI system is. And that actually brings up something that's not on the slide here. If you think about it, right? Industry, one of the ways of industry getting better and better systems is competition. Competition also in an economic sense, right? But competition doesn't work if you can't compare systems, if you can't tell which system actually is better than the other, right? Competition only works once you can say that. And so this validation, this measurement of how trustful, how safe an AI system is really fundamental also for the economic progress in AI and for establishing mechanisms to bring us forward. Once we have that, I think it will become like a self-fulfilling prophecy then. I mentioned that there's a lot of HPC needed for this, and we need better tools for that. And but towards the end, I want to really make sure this is not finished research I was talking about. This is essentially our longer term research strategy. There is still a lot to be done, many challenges that we need to overcome, which requires actually much closer collaboration with industry and academia, and DFKI is doing many novel and innovative ways of how we can collaborate with industry. And I believe that we don't just need to do this within one organization, but this really requires, we really need to get the brightest mind in each of those areas. And what I talked about is just one, there's many, many more. We need to get the best minds in Europe together, and that's what we're trying to achieve with CLAIRE. With this, I think there's a lot of work that we need to do, and I'm happy to collaborate. We're very open to collaborate within CLAIRE with DFKI. So if you have any questions, I'm happy to answer them now, but also feel free to contact me after this if there is some interesting stuff to talk about. Thank you very much.
Hi. Philip, thank you very much for this very exciting talk. I will be now the person who will ask the question for the public. There are questions, but I totally agree with you that digital reality is the future for AI. So now comes question from the audience. Jose Maciel de Medeiros. So, dear Philip, can we use synthetic data in the optimization of industrial processes? Question mark. If we have a problem with data availability, how can we train models to generate the data that we cannot get from certain industries? Question mark. That's his question.
Yes, absolutely. We're actually doing this. So I can't talk about what the customer here is, but it's about chip production, so electronic chips. But the packaging, these packages sometimes have cracks, but actually only very rarely. But if they have cracks, this needs to be detected. They're very subtle, small cracks, And we've done a very exciting project there with a big company where we actually created models of these cracks and the appearance of the objects as well as the cracks. And then we generated large numbers of synthetic cracks, if you want, synthetic failed parts. And we use that for training with very, very good success. So there's a lot of, we do a number of other projects in this area. So I think there's a lot that can be done in this direction. In this specific project, there was a lot of manual work in creating these models. But I think we could have used much more AI to automatically learn those models. So we're really only at the beginning of using this technology.
Okay, thank you.
As I said at some point, right? Whenever you can model the environment of an AI system, that the environment that an AI system interacts with, you're in good shape and you should be able to use it.
Okay. So another question, because time is running. Instead of modeling for all kinds of obstacles, could you model for no obstacles? This question comes from Bjarke Nielsen, and it goes on. So just listen, I can repeat. Recognizing only a free road, question mark, question mark, question mark, stopping also for baby strollers and other non-trained objects. And yeah. Continues, which institution should be responsible for validating and certification? So we have a lot of questions. I can repeat, but
yeah, of course. I mean, we can also, and that's actually something we're also working on. Essentially, there was a project we've been engaged in where we stochastically generated new roads as we were driving. That was very interesting. It was primitive in some sense, but you can make this much more elaborate. It's something we're working on. So yes, and you can have those roads can be empty. If you want to train more for detecting persons, you can put lots and lots of pedestrians on there. If you want to train for detecting animals, you can put animals in there, and so on. You can really tailor this for your specific target. You can also say, well, I use some standard, I keep all the parameters fixed, I only vary the number of pedestrians or animals or whatever. So there's a lot of stuff you can do in this direction. The other question was about who should be doing this certification. That's actually a very interesting question. So there is a lot of interest by some industries doing this. So we actually collaborate with the German TÜV, which is doing certification of cars already. They were actually founded to prevent accidents for steam engines when they came up 150 years ago. And they see a huge potential now to make sure that AI systems don't blow up. So we're working with them, but there's many other interested parties in this. There is now the politics, at least in Germany, but also in some other countries, are looking into this. As far as I know, and we're talking to some of the key people here in Germany, there will actually be an official ministry, part of a ministry that will look into this, and we're doing some work in this direction as well, together with them. We're exploring this, I should say. It's not, the project hasn't started yet.
Thank you. Yeah, as I say, now I'm talking even faster. Another question, Faiz Ikra Mullah. Thank you, very insightful, dear Wilselek. First of all, thank you for insightful presentation. Do you think that developing a virtual brain, actually a hybrid brain, as an artificial intelligence and human intelligence interface for hybrid intelligence-based decision support system could be an approach to capture high accuracy in, I'm going on, one moment, in predictions?
I'm not entirely sure if I understood this correctly. We're not trying to build brains. I think that's a huge point. We're building tools, right? We're not interested in building artificial humans. Why on earth should we do this? For me, AI is a tool. It's always the humans that use the tool, that build the tool, that deploy the tool, or use the tool, who will be responsible. I don't think it makes any sense to build an artificial system, right? You run into all sorts of problems if you try to legally, ethically, and in many other aspects. And why on earth would we try to replace ourselves, right? I mean, it's us to experience this great world around us, but there's certainly things how we can make our life easier, nicer, and in many other aspects improve our lives. And yes, AI can play an important role there. I see also a very important role of AI to understand our human thinking better by modeling this, but I don't see much use in building artificial brains.
Yes, thank you. This was actually from Hasan Susen, because there's a mix up here from, was like, sorry, Hasan, this was actually yours. And now comes Faiz Ikramullah. Could you briefly list a few of the metrics for quality or benchmarking that you currently use for AI systems?
So for autonomous driving, of course, a very basic measure is don't hit pedestrians, don't even barely hit pedestrians. It can be often very simple things like this. Also, you want to optimize for right, a smooth ride. Don't wiggle around with your steering wheel. Don't accelerate and brake all the time. So minimizing this is an important step forward. Staying on the lane. So there's lots of criteria that are being optimized at the same time without going too much into detail. But of course, this is always something that that is very application specific. So for autonomous driving, these are obviously very different approaches than if you want to optimize for less cracks in chips. Yes. Yeah, I guess that's what I can say for that.
Okay, I think we are out of questions here from the public. But also due to time, we are now closing down this great session today. I thank again Philipp Suselek. I must say he's a great friend. So personally, I'm very enlightened to have you here on air. And I love to continue research together. And I wish you all a nice Wednesday. We are now closing in a few minutes, and I take this chance again to ask you, if you would like to be a speaker in this cafe, please apply to me. You have my email in the handout. There are handout. There's Philipp's and my presentation as a handout. If you like, you can have it. And there will be recording available. This recording first, Philipp has to say it's okay, then it can be distributed to the participants. So take a moment, wait, and if you like to have it, you will get it. And again, we have great web cafes coming up. I will, as always, per email inform you. And if you don't want to be on the email list, just drop another email. I don't want to be informed anymore. You are out, it's fine. But I'm very happy you're all there. Take the chance to present yourself. This is the networking space to share knowledge in Europe. Thank you very much, Philipp. Thank you. And
thank you for inviting me, Carmen. I think it's a great pleasure doing this. And again, if anyone, if there's interest, drop me an email or whatever. Email is usually the best way to reach me.
Yeah, and it's in the handout. And just ask me, and it's all fine. So have a nice afternoon. Bye-bye, everybody, and see you hopefully soon.
Bye-bye.
Bye-bye.